You could use MPU to prevent any kind of limit memory access, but usually it's difficult to configure. It's not very dynamic. If you add new threads, etc., you need to modify the configuration of the MPU.
Hey guys, welcome to Embedded Toolbox, the video interview series where we try to save the world by solving one engineering challenge at a time. And one engineering challenge that we're hoping to solve today is allowing engineers who are working with small microcontrollers to take advantage of some features of virtualization like sandboxing in their development environments. And to help us navigate that challenge, we brought on Jerome Leroux, who is the CTO of MicroEJ. How you doing, Jerome?
Good, thanks. How are you?
I'm doing well, thanks. So what are some of the benefits of using virtualization in your development environment?
Yeah, so when you're developing a microcontroller with an RTOS, so you don't have any MMU, no Linux, one issue you can experience is a crash of the whole system because of basic bugs. You can have also bugs that are very difficult to identify. For example, just yesterday, I had a coworker who wasted several hours with a function was returning weird values. And the cause of that was a stack overflow in FreeRTOS. So the stack size of this task was too small, and there was a memory corruption. Other causes for such kind of bugs could be invalid pointers or any corruption of data. And thanks to the sandboxing, we can control what application can access and limit the effect of such kind of issues.
So as you mentioned though, Jerome, there are a lot of devices that don't have an MMU. So in those instances, which is not uncommon for an embedded engineer, what are their options?
So at MicroEJ, we have a MicroEJ virtual execution environment, MicroEJ VEE. It's a software container that can run on both microcontrollers and microprocessors. And when you are on microcontrollers, this software container will provide a kind of virtual and software MMU. I can show you some slides. So the MicroEJ VEE, this software container, provides a virtualization layer on top of an RTOS or an operating system. And it includes a virtual processor called Mesh32 that is in charge of executing and sandboxing the application that runs on top of it. And we have two layers of sandboxing here. One is a MicroEJ VEE itself that will prevent all the software that runs on top of it to access directly to the hardware or the drivers, and prevent it to corrupt the whole system. And the second layer of sandboxing is the application layer, where you can have several applications running on top of the MicroEJ VEE, and each application is sandboxed, so it cannot access code or memory data of other applications.
Well, that looks good in theory, Jerome, but let's see if it works in practice. I know you've set up a demonstration for us today of MicroEJ VEE. Can we take a look at that?
I run the MicroEJ SDK, so that's an IDE based on Eclipse that allows to develop applications that we run on the MicroEJ VEE. Here I have an application, Java application. That's a watch face that will run on an RT500 board from NXP. So that's a microcontroller Cortex M33 that runs at 200 megahertz. And first I can...
have it with you there, just to make sure you're not doing any vaporware, Jerome.
Yeah. Let me show you that. So that's the board with the microcontroller. And there's a circular display here. Thanks to the virtualization and the software container from MicroEJ, you can run your application actually on a simulator. So you don't need the actual hardware to run it. So we just use the application itself running on the simulator. I can start that from the IDE. And on the simulator, we are simulating the hardware. So we have a picture of the development kit. And we are simulating the circular displays, the touch screen. So here we have a touch screen, and we can control it with the mouse. And that's a watch face I've just developed, a basic watch face with just 3 hands here. We are simulating the button. So if I press on the button, I can go to the main menu. And now I will install dynamically this application to the device. And so I have here the same application that runs on the device. So there are only 3 watch faces here, and I will add a new one dynamically. So what I need to do is to build the application, and then from the serial terminal, I can set it so the board is connected to my PC through a USB cable, and I can upload the application through USB. And once the application is uploaded, it will automatically install it and start it. So here we have a new application that has been added dynamically to this microcontroller. And now we have 4 watch faces on the system. I can restart it, stop it, and even uninstall it with a long press. You can remove the application. So now what we'll do is we'll add a few bugs to this application. So
yes.
here there is
let's try to break it.
Yeah. So here there is a start method that is called when the application is started. And if I change the code here to create an access to null, so here this field is initialized to null, and I will call a method, a Java method on it. And let's see how the system behaves. And so the kernel will install the app and tries to run it and start it. And we have here a null pointer exception that is thrown and called by the system, and will prevent the application to start. So the system still runs, so I can select another watch face, go to the main menu here, etc. And I can try to relaunch the application. If I click on it, I'll get again this null pointer exception here.
Great.
So let's uninstall the application. And now what we can do is demonstrating another typical issue you can have on microcontroller. I mentioned stack overflow issues. So what we can do is here there is a hook. I can remove that. There is a method that is called when you are clicking on the watch face. So if we detect a click event here, we can print a message. And what we will do, we add a bug here, just call the same method here. So we have this handle event method that calls itself. So it's a recursive call without any end, and it will should cause a stack overflow. So we build that again. So now the application can start, but if I click on it and get the click event, I get this big stack trace because with all the stack frames. And so we have the click event here and a stack overflow that is printed. That is caught, and we are printing the stack trace here. And automatically the application stops, and the system is still up, and we can select another watch face.
That's great.
So that's typical issue you can have with microcontrollers in C. If you do the same thing, you get a crash of the system. You could use MPU to prevent any kind of limit memory access, but usually it's difficult to configure. It's not very dynamic. If you add new threads, etc., you need to modify the configuration of the MPU. So here it's built in the system. We have this kind of virtual MMU or MPU that will help you to debug your issues. If we create a new instance, so we name that watch face 2. So we create another instance of the same application with a different name to distinguish it from the first one, that will access the same counter value. So this global value, it's the same class name. So we have here the same class and same code for the 2 applications. And if so we have started the first watch face, you can see it running. And if I install the second version of the application, we have here now on the board two identical watch faces, and both watch faces have their own daemon thread that runs in the background and incrementing the counter. So we can see that the counter value is local to each application. So there is a sandboxing of this global value, and one application cannot access or modify value that is owned by another application. And if I stop one application or install one application, yep, I installed it. So the first one still running. Can install both here. So that's typically an example of data sandboxing, also code sandboxing, because here we have two classes with same name, the same classes, but we have two instances of these classes that are embedded in a system and that are independent. So we can install, upload, install, and uninstall this code. We can have one version of a library for an application and another version of the same library for another application. So all these applications are really sandboxed.
That's some impressive stuff, Jerome. Thank you so much. But before I let you go, I got a couple more questions for you.
Yes.
The first one is, so that simulator, does MicroEJ have different simulators for other targets that are available for developers to use?
Yeah, so when you are porting the MicroEJ VEE to a specific hardware, you need to implement an abstraction layer that is specific to the hardware, typically as drivers, etc. And so that will be the code, the runtime that we run on the device. And in parallel of that, you can customize and develop your own simulator, the configuration of the display, resolution, number of colors, and stuff like that, that you can simulate with the simulator.
That's great. And also, obviously, we're working in Java here today. A lot of embedded developers don't work in Java or work in Java and other languages, notably C. Is there anything like this available for other languages, either now or coming down the pike in the future?
So for now, we are supporting Java and JavaScript, and we are in the process of developing support for C. So that's we have a beta version of managed C. So the C will run in the sandbox too. So any issue in the C won't jeopardize all the system. And that's something we are working on. And we have planned to add more languages like Kotlin or Python later.
That's great. Well, if developers are interested in going and learning more about MicroEJ VEE and your support for all these languages, either now or in the future, where should they go?
So we have a developer website. It's developer.microej.com, and you'll get all the resources, documentation, demo, videos, the presentation of all the MicroEJ products.
Great. Well, thank you so much, Jerome. I really appreciate your time, and hopefully we can have you back on soon when you're done with that managed C version.
Yeah, sure. Thank you. You're welcome.